Hey guys, so this is going to be a lecture video for the next unit, which is food webs and trophic levels. Um, Sorry about the glare of the lights, but if I turn them off, then you can't really see me. And I look okay, so deal with it. Yeah, so we're going to be talking about a little bit of nutrient cycling, food webs and chains, as well as trophic levels and how they're associated with each other today. Okay. Um, So yeah, let's just get right into it here. Basically, the first thing we're going to be looking at, main concept, food chains versus food webs. Um, while they do show the same general idea, there are some differences we're going to take a look at. So basically, we have food chain, right? As you can see, the picture on the far right, and the food web is the picture next to it. Um, Food chain is going to be more systematic and linear, versus a full web is going to be, it's going to show you all pathways of energy flow throughout a community. So there's two definitions here. The first one, relationships between animals and the ocean and how they exchange energy systematically. So like I said, systematically linear is going to be that picture on the right. That's going to be the definition of a food chain. Keyword there, systematically. And then the bottom one, relationships between animals and the ocean that represent multiple pathways for energy to flow. Okay, so in the picture on the right, we see one energy pathway flow from the bottom to the top. Picture next to it, not so much, right? We can go from multiple ones. We can go from the phytoplankton, right, to the fish. We can go from the phytoplankton to the tuna. There's multiple pathways there of energy flow, okay? Also, food chains and food webs. I put this in here about the ocean. It doesn't necessarily have to be for the ocean. Food chains and food webs can exist on terrestrial environments too, in communities. So it can just be the relationship between those animals, not necessarily just in the ocean. But for our purposes, I put that in there. Okay. Next part here, we're going to take a look at the trophic levels in these food chains. More specifically, it's a lot easier to kind of talk about it in a food chain that's more systematic and linear. So the first trophic level we have at the very bottom, these are going to be our producers. Producers create their own energy. They don't have to like eat anything else or digest anything, right, to get the energy they need. They get it from two main pathways that we're going to talk about today is either photosynthesis or through carbon fixation. The next level here is going to be our first level is the primary consumer. Primary consumers. Hopefully you guys can kind of put those two together, but right, our primary consumers are going to eat the producers. That's how they get their energy. Next one, pretty self-explanatory. Secondary consumers. Those are going to be eating the primary consumers to get their energy. And then the last one, tertiary consumers. Just the next level up, right? So as we go up, we can see what eats what. Basically, everything other than the producer is a consumer, and then we're going to get into decomposers later as well. But everything that's not a producer or a deconsumer is going to be either primary, secondary, tertiary, or there's other multiple levels of consumers that we're not going to go into in this part of the class. Okay. So this can also be represented in a pyramid. This kind of helps me imagine it a lot better in the aspect of numbers of organisms. So within our oceans, hopefully you guys know this, but there's a lot more like unicellular. If you look at a cellular level of organisms, there's a lot more like algae, seaweed, producers like that do photosynthesis than there are things like krill in the next level, Finding Nemo. I'm blanking on his name, Marlin, and then sharks, right? So we have a lot more at the bottom of the food pyramid than we go to the top. Okay. Another thing we'll kind of take a look at here is we're going to take a look at these numbers here on the left. Basically, this is called the 10% rule. So the 10% rule, actually, I'll explain this first. 100, 10, 1, and then 0.1 and the J beside them stands for joules. For those of you who don't know, joules is a term, is a unit for energy, and the unit is meters per second times kilograms over second squared. It's basically newtons per second squared, is how it's calculated. That's kind of hard for me to imagine even. All right, there's 100,000 joules in a kilojoule, and it takes 1 kilojoule to heat a cup of room temperature water to boiling. So if you can kind of, I don't know how you really picture energy in your head, but you can, right? You can picture a cup of water like going from room temperature to boiling. That's how much energy is in 100,000 joules. So, right, in the whole grand scheme of things, it doesn't look like we're talking about a lot of energy that's going on here. I just made these numbers up. I don't know if these are actually true. I didn't do enough research into if algae produce 100 joules worth of energy or not. So do not take these verbatim for what they are. Also, another unit, right? We talk about calories in food. 1 calorie is 4.2 joules, approximately. So just a couple ways for you guys to try to imagine how energy is flow throughout our communities and our food pyramids. Okay. Yeah. So we'll go back 10% rule, right? Our producers create, in a perfect world, 100 joules of energy that they have stored in glucose, other things within their cellular structure. The krill that would eat those algae and seaweed and other things only regain about 10% of that energy from the level before it. So of the 100 joules of energy that is created by the producers, when the krill eat the jewel, when the krill eat the algae or whatever the producer may be producing, they only get 10% of that. So they would only get 10 joules worth of energy from it. Same thing for the next level up, right? Fish that eat these smaller organisms in the ocean, they're only going to get 10% of that level as well. And then you can go all the way up to the sharks, right? You can kind of understand now, right, why sharks have to eat so much is because they only have a limited, like they can only harness a certain amount of energy from each of the fish that they eat. So they have to be continuously eating to have that energy in their body to do what they're built to do, right? So hopefully that makes a little bit more sense to you guys. 10% rule is going to be big, and then kind of a little explanation on joules and how that unit kind of works. Okay. So we're going to get into like a little bit of these producers, autotrophs, consumers, and stuff like that. So the first one here is producers and autotrophs. Producers and autotrophs can be used, can be exchanged with one another. It means the same thing for what we're talking about. Yeah, like I said earlier, guys, we create organic material from inorganic material, right? We create light. We do not create light as a producer, sorry. We create energy in the form of glucose from light. It's called photosynthesis. Hopefully you guys know the photosynthesis equation, which we're going to talk about the photosynthetic cycle here in a little bit. But yeah, they create energy either from light, from the sun, or from carbon dioxide by a process called carbon fixation. Okay. This is what producers and autotrophs are going to do. There's multiple ways for, there's things like chemotrophs, which can create energy from heat as well. But these are the main two we're going to be talking about, is the light to energy and carbon dioxide to energy producers in our oceans. So these producers and autotrophs are going to be using this main system here to create their energy with. So the picture in the middle there is kind of representative of what algae, seaweed, like that's what it is. So we have two ways that can be happening, right? The top arrows basically are the photosynthetic cycle, and the bottom is more aimed towards carbon fixation, but they can all be used in it like interchangeably, right? So photosynthetic cycle, we have, I don't know why I put photosynthetic cycle if I talked about carbon fixation here, but we're just going to roll with it. Light energy right from the sun is going to be taken up by the chloroplasts in these organisms. These chloroplasts are then going to create glucose, which then can be used by our primary consumers when they are uptaken by them. Okay, the bottom one there, CO2 by either fish breathing throughout the, yeah, actually, this is the photosynthetic cycle. I don't know what I was talking about. I guess I should go over the photosynthesis equation, right? I mean, hopefully you guys all know this. 6 CO2, 6 H2O, and then we get a glucose C6, H12O6, and 6 O2 from it. So we need both light energy and CO2 to create glucose and oxygen. So we can get carbon dioxide in different forms in our oceans. We can get it through either fish breathing, right? Exhaling, or there's other vents in the bottom of the ocean that kind of create CO2 as well, underwater volcanoes basically that bring up carbon dioxide from the earth. And then they create oxygen, right? For life to exist in the ocean, we need there to be oxygen there so we can have our fish breathing and other mammals as well. Okay, so that's kind of a little bit about photosynthetic cycle. Yep. Okay, so next we'll be talking about the heterotrophs. Heterotrophs are going to be our primary, secondary, and tertiary consumers. These organisms, like I said earlier, cannot produce their own food. They are dependent on others, can be dependent on the producers or other heterotrophs, right? Our sharks, for example, are not going to be dependent on producers to create their specific food for them. In the whole grand scheme of things, right, they are dependent on producers to sustain life for the other fish that they may eat, but they're not directly dependent on those producers. Okay, they require complex organic substances that are going to be created throughout their body, right, to uptake that energy. They're going to take it in the form of glucose, but then they have to convert that glucose into other substances in their body to use it, basically. Sort of, kind of. I mean, they use glucose, but they also use other things as well. Okay, use other sugars and whatnot. Other important thing here is decomposers. These are not usually included in our food chains and food webs because they kind of make it messy, but it's nonetheless, it's a very important part of the food cycle or the food chain and web and the whole cycle that's happening in our oceans. I mean, hopefully you guys know, right? We have things like worms and slugs and stuff like that that are decomposers on terrestrial environments, but we also have them in our oceans as well. They help break down organic material on the ocean floor. Again, one of the most important aspects of an ecosystem. This helps, this picture, which I know it looks like I got it from Google Images or took a picture of the ocean floor, but I actually photoshopped it. So I don't know, might do photoshopping on my spare time. But if we have a bunch of dead fish just pooling up on the bottom of the ocean floor and we don't have decomposers, then you can see how that would create a lot of problems, right? There's a lot of dead fish just pile up at the bottom of the ocean. There's not a lot of good that comes from that. Yeah, it would just create a whole mess, basically. So some examples of some decomposers that we see in our oceans are going to be things like marine worms. There's even fungi that live on the bottom of the ocean floor. Some crustaceans also decompose materials, slugs, and mollusks as well. Okay. Last one here, the carbon cycle we're going to talk about a little bit. A couple important things before we kind of get into the cycle of this. There's 50 times more carbon dioxide in our oceans than in the atmosphere. Okay, and this leads to 90% of our total carbon dioxide on Earth being inside our oceans. So that's actually a lot. We think we have a lot of carbon dioxide in our atmosphere, but 90% of what we have is going to be in our oceans, okay? The other important thing to know, not all carbon is bad. Carbon in the form of carbon dioxide is not great, but carbon is basically the backbone for life as we know it. Without carbon, we wouldn't have life, and it exists in all cycles of life, not only terrestrial environments, but also marine as well. If you guys take any chemistry classes, you guys will kind of see this. I took a couple classes about organic chemistry, where we do carbon skeletons, basically, of different substances, and all organic substances which can be used to help create life and that are broken down by organisms have this carbon skeleton on them. So carbon, as we know it, basically is the backbone of life, which is what I'm trying to get at, I guess. Okay, so this carbon cycle here, we're going to first look at the fish, right? We start in the ocean. As you can see, when I click the button, we have sedimentation happening. So when we have dead algae, fish, any form of organism, they all sink to the bottom, right? What doesn't get eaten by decomposers then is slowly eroded away, even in the ocean floor. When this happens, it's very compacted, and this over long periods of time creates oil, coal, and natural gas in our Earth. Okay. How do we get that? I mean, humans extract it, obviously, and then the other way that can get there is by sedimentation of things on Earth as well, in terrestrial environments. So not only of the ocean, but also of animals on Earth. That slow compaction and sedimentation process creates the oil, coal, and natural gas that we basically use all the time. Okay. This human extraction, right, is going to create fossil fuel emissions. That's not going to be great for our environment, but nonetheless still happens. We also get not necessarily oil and coal and natural gas, but we get carbon dioxide, as I said earlier, from volcanic eruptions that happen. And this is supposed to, I think I exited or blanked this out because it's obviously fossil fuel H emissions, which it should be emissions. So yeah, we have CO2 being created and taken up by the photosynthetic cycle, as well, as we can see in that picture with the tree. And then we have constant diffusion happening, right, of the CO2 that's in our terrestrial environment and in the atmosphere is continually happening with our oceans as well. Okay, so I think this carbon being the backbone of life, basically, I think it's important to recognize the carbon cycle and how it's being cycled throughout our oceans, as well as throughout our atmosphere and the world as well. Okay. So that's basically everything that I have for you guys on this. This unit is going to be very similar. The assignments aren't the same, but very similarly structured to last unit. So hopefully you guys watch this and then you take what you know from this lecture video and do your assignments with it. We'll do the lab in class, but hopefully you guys have watched this before coming to class. So if you guys would, nope, you've already watched the video. Never mind, I was going to say take the pre-quiz, but you guys have already watched it, so that wouldn't do you any good. Unfortunately, and I don't have a good way of, I have a good project for you guys this unit, but I don't have a good way for varied assessment like I did with the ecosystem. So I think I'm just going to have you guys do a quiz that's very similar to the pre-quiz, like the ecosystems unit, for your end of the unit quiz, unfortunately. So I'm sorry about that, but I couldn't come up with a good idea on how to do that for you guys. Yeah, so if you guys, again, have any questions, take a look at the material on any of the assignments. Go ahead and get those done sooner rather than later. If you have any questions, please, again, do not hesitate to email me. I've had a couple emails from people asking questions about Canvas and stuff, and it gives me something to do. So don't hesitate to do that. Or reach out to me or Mr. Livingston. We can get some of those questions answered for you, whether it be on how to get to an assignment, what this assignment is, or I don't understand this concept. We can explain it better for you. Okay. I think that's everything I have. Tried to keep this one shorter, so I don't know what the time is on it, but we'll let you guys go. Okay. See you guys in class.